Thank you so much for joining me today. So in today's lecture, we're going to really do two things. The first thing we're going to try to do is think through how to solve optimization problems when people's budget constraints aren't standard, which is to say that when the price you pay for one good or another changes based on how much you pay, right? You're not dealing with a situation where you pay one fixed price no matter how much you buy. And then once we've done that, we're going to shift over from thinking about individual specific optimization problems to using the tools we've developed, these consumer optimization tools, to understand how quantities demanded change as prices change and as incomes change. So we're really going to be able to shift from analyzing the decisions of an individual in a specific circumstance to starting to build tools that will allow us to analyze markets more broadly. Okay, so in this video, we're going to focus on this first question, which is how to solve problems when we have kinked budget constraints, which is to say budget constraints where the prices we pay for a good change based on the amount that we purchase. And these problems are really important. We run into them all the time in the real world. So as a consumer, you've probably run into a bulk discount at some point, right? You've got a 2-for-1 special, or once you've bought 10 coffees at the coffee place, you get your 11th coffee free. All of these are things that effectively lower the price of a good if you buy more of that good, right? And sometimes we also run into the opposite problem, where prices get higher as you buy more. So for example, maybe the first month of cable is going to be cheaper than the second month, right? We have something like this. So these are important to understand from a business and consumer side. They're also maybe even more important from a policy perspective. And the reason for that is that a lot of the programs that we have to support low-income households are going to take the form, or do take the form, of subsidizing the purchase of small quantities of a good. So one example, there's a home heating program to support low-income families in cold parts of the country that subsidizes small amounts of heating fuel, but as you buy more and more, the subsidy goes away. We might think about food stamps as doing a similar thing, or various other programs to support housing or food purchases. Even more importantly, we can think about income support programs like the Earned Income Tax Credit and progressive taxation as effectively changing the effective wage rate people earn as they work more hours. And so when we think about the problem facing a worker of how many hours to work, these kinked budget constraints where your effective wage is changing as you change the number of hours you work, is going to be very, very important. So as policy, right, as people who want to think about policy and understand policy, knowing how to solve problems when people don't face a constant price is going to be very important. Okay, so let's start by thinking through an example where you pay a lower price for small quantities in an item than you will for larger quantities in an item. In other words, where the first couple units are discounted relative to later units, right? So like getting a discount in your first month of cable. And to think about this, let's go back to our froyo example. And imagine that we've got, let's say, a $10 gift certificate. And we've got, normally we've got prices of $2 an ounce for toppings, and $1 an ounce for froyo. But we also have a discount, right, a special deal, where for the first 4 ounces of topping, first 4 ounces of tea cost just $1 an ounce. Right, so you pay $1 an ounce for ounces 1, 2, 3, and 4 of topping. If you wanted to buy a 5th ounce of topping, that would then cost you $2 an ounce. Cool. So let's think about what this is going to look like. And to do that, let's draw a graph where we'll put topping on the vertical axis and froyo on the horizontal axis. And let's think about the crucial points on this graph, right? So let's think about the intercepts, right? How much froyo you can get when you buy no topping, how much topping you can get when you buy no froyo. So let's start with the froyo intercept. Right? So this one's relatively straightforward, right? You've got $10, froyo costs $1 an ounce. So if you spend all your money on froyo, you can buy 10 over 1 equals 10 ounces of froyo, right? Okay, great. How about the topping intercept? So this one's going to be a little bit harder to think through, because the price that you pay for topping is going to depend on how much you buy, right? So we know that for the first 4, you can buy 4 ounces of topping at $1 an ounce, and that's going to cost you $4, right, for first 4. That leaves you with 10 minus 4 equals $6, right? And then you can buy, let's say 6 over 2, right? Because now you're paying $2 an ounce, is 3 ounces, right? So what's your total amount of topping if you spend all of your money on topping? It would be 4 plus 3 is 7 ounces of topping, right? So if you spend all of your money on topping, you can get up to 7 ounces of topping. Cool. So now that I've done this, can I just draw a straight line between 7 and 10, like I would in a standard problem? No, right? That's not going to be right. Because if we think about what the slope of our budget constraint means, right, it's going to tell us our price ratio, right? The price of froyo over the price of topping. And that slope should be different when we're paying the discount, right, for our first 4 ounces of topping than it will be for our last 3 ounces of topping. In other words, our budget constraint is going to have a different slope early on than it will later. So we need to find one more point, which is our kink point, where the slope changes. What's the idea behind the kink point? The idea behind the kink point is we're going to have a different slope when we've bought fewer than 4 ounces of topping than when we've bought more than 4 ounces of topping, right? So at 4 ounces of topping, right, our slope changes. So all we need to know where this kink is if it's going to be at 4 ounces of topping, how many ounces of froyo? So how much froyo? When we have 4 ounces topping? Well, it's just going to be 10 minus the cost of 4 ounces of topping, which is going to be 4 times 1, right? Divided by the price of froyo, which is 1, so it's going to be 6, right? In other words, we're going to have a different slope, right? When we've bought fewer than 4 ounces of topping, and therefore more than 6 ounces of froyo, than we will when we've bought more than 4 ounces of topping, and therefore less than 6 ounces of froyo. Cool. So I'm going to draw this budget constraint now, right? Otherwise, it's just going to be straight lines. So I'm going to draw this budget constraint by using a different color above the kink than I will below the kink. Great. And what's the slope of our budget constraint going to be? Well, it's going to depend on which piece of the budget constraint we're on, right? But in each piece, it's just going to be the price of the horizontal good over the price of the vertical good. So the slope here is going to be PF over PT, right? It's going to be 1 over 1 is 1. And the slope here is going to be PF over PT is going to equal 1 over 2, right? Cool. So what does this mean? It means that when I haven't bought, when I bought fewer than 4 ounces of topping, I have to give up 1 ounce of topping to get an ounce of froyo, right? After I bought 4 ounces of topping, if I had 5 or 6 ounces of topping, I'd have to give up half an ounce of topping for each ounce of froyo. And why did we call this a convex kink? Because if we drew a line between any 2 points that are feasible, the average between them would also be feasible, right? So this is going to be similar to how if we draw a line between any 2 points on an indifference curve, when more is better, right, the combination is going to be above that indifference curve. So essentially the set of feasible things is going to be a convex set. Cool, okay. So this is what this looks like. Let's think about how to solve problems. Right, so if this is what our budget constraint looks like, let's think about what the solution to an optimization problem has to look like. So in a normal optimization problem, right, if I have a standard budget constraint, right, something like this, there's 3 places where I could find a solution, right? I could find a solution at the vertical corner, I could find the solution at the horizontal corner, I could find the solution somewhere in the interior, right? We have either a corner solution or we have an interior solution. So when we have a budget constraint like this, we're going to use the same logic. It's just that we really have, instead of 3 spots broadly defined, right, on our budget constraint, we're going to have 5 spots. Why 5? Well, I can have a interior solution, a blue interior solution, right? Meaning that I want to buy something between 4 and 7 ounces of topping. I could have a red interior. We could have a solution somewhere here, or we could have a horizontal or a vertical corner, or our optimal choice could be right at the kink point, right? So essentially we've got, for each segment of our budget constraint, we have the corners that we're used to, or we could have a solution somewhere in the interior of our budget constraint. So that's kind of a lot, right? That's a lot more than we're used to. But let's think through how to look for each of these 5 types of solution. And let's start by thinking about specifically the interior solutions, right? So if I had, let's say, a red interior solution, what that would mean is that I have preferences that look like this, right? And my best choice would be somewhere where if I wanted to, I could buy more or less froyo at a price, right, of $1 per froyo and $1 per topping. But I end up with an indifference curve that touches my entire budget constraint just at one specific point. And so what do we need mathematically in order to have an interior solution? Well, to have an interior solution, right, we just need 2 things. We need that our MRS equals our price ratio. And we need that we're on our budget constraint. So if we want to look for an interior solution, right, so these 2 conditions, right, that we have our MRS equal to our price ratio, and we're on our budget constraint, are also going to hold for this problem, but working with them is going to require a little bit more legwork than it would in a standard problem. And the reason for that is, so far we haven't written down our budget equation for this strangely shaped budget constraint. And in some ways what you could think about, if you wanted to write down a budget constraint that looked normal, right, that looks like a set of linear equations, essentially what we have is 2 budget constraints, and we need to satisfy both of them. Right, we can think about this red budget constraint as continuing to extend outward, right, and this blue budget constraint as continuing to extend outward. And if we wrote down the budget equations of each of these 2 budget constraints, then essentially what we would need is to be in a red interior solution, that we've satisfied this bigger red budget constraint, we are equal to the price ratio for the red budget constraint, and our optimal choice is somewhere below the kink. Right, in other words, the way I drew this indifference curve here would in fact be an optimal solution, but if instead I'd drawn an indifference curve somewhere like this, this would not be an optimal solution, right, because it's not actually feasible for us. Okay, cool. So let's figure out what our red budget constraint should be. So we know the prices, right? We know that it's got a form that looks like PF times F plus PT times T is less than or equal to I, right? And we know that in the red part, right, our red prices are 1 and 1, right? We also know that our income has to be just enough for us to buy 10 units of froyo, right? So income is going to equal 1 times 10 units of froyo equals 10, right? So our red budget constraint is going to be F plus T less than or equal to 10. Okay, so then when we try to solve this problem, right, what we're going to do is first we're going to find our MRS, set it equal to our price ratio, and then check to see whether we're inside this budget constraint. Right, so we've got some combination of F star and T star that are a solution if, right, the MRS of calculated F star and T star equals PF over PT, red PF over red PT, which equals 1, and F star plus T star equals 10, and, right, T star is less than or equal to 4. In other words, we're in the real part of our red budget constraint and not this fictional part that we constructed up here. All right, with me so far? I hope so. If not, please put a question in the Moodle docs or ask. Okay, so this is the red part of our budget constraint. To look for an interior solution in the blue part of our budget constraint, we're going to do exactly the same thing, right? We're going to construct our blue, we're going to figure out what our blue budget equation is, right? And then we're going to look to see whether there's a solution where our MRS equals our blue price ratio when we're buying more than 4 ounces of top. And how will we construct our blue budget constraint? I won't walk through the whole process again, right? But we're going to do the same thing. We're going to say we know that our prices are PF equals 1 and PT equals 2. So we're going to say 1 times F plus 2 times T less than or equal to I. And we know that we can afford 7 ounces of topping, right? So we know that 1 times 0 plus 2 times 7 less than or equal to I, or equals I, right? And therefore we know that our income is going to be 14. So our blue budget constraint is going to be, right, F plus 2T less than or equal to 14. And we'll have a blue interior solution if there's some point where the MRS calculated at that point is equal to 1/2, right? And, sorry, this should be 1/2, is equal to 1/2. And we have F plus 2T equals 14. And, right, we have more than 4 ounces of top. Okay, cool. So this is what we're going to do for our interior solutions. It's a little bit more legwork. We have to really think graphically, but it's more or less what we're used to. So how about corner solutions? So as we talked about before, right, we have 3 different corner solutions to worry about in a problem like this. And the first 2, right, the vertical corner and the horizontal corner, are relatively standard, and we're going to be able to approach them in more or less the same way that we would approach a corner solution in a normal problem. Which is to say, right, if we think graphically, if we're at a vertical corner, we need to have our indifference curve through that corner, right, be entirely above our budget constraint, except for at that corner. And what that's going to mean, right, is that it's going to have to be less steep than the budget constraint at that corner, right? So vertical corner is going to be their MRS calculated at 0 and 7, right at the corner, has to be less than or equal to our blue price ratio, right? Or 1/2. And our horizontal corner, right, if we're going to have a horizontal corner solution, we would have to have an indifference curve that again is entirely above our budget constraint except for at that corner, which means in this case it would have to be steeper, right, in order to dodge our budget constraint. So for our horizontal corner, right, we would have to have just that our MRS, when calculated at our horizontal corner, right, 10, 0, has to be greater than or equal to the price ratio at the horizontal corner, i.e. the red price ratio, right? Okay, so far so good. Nothing too wild here. But how about this last corner? What about this kink point, right, this middle corner? So let's think about what has to be true for that to be our optimal choice. So let's imagine that I have an indifference curve like this. Is this my optimal choice? Yeah, right, it's my optimal choice because that kink point is the only point that is on or above that indifference curve, right? Everything else that's better than the kink point is not affordable to me. Everything that's worse than the kink point is, everything else that's affordable is worse than the kink point, right? So this is in fact my optimal choice. But I could draw it in a number of different ways, right? It doesn't have to have exactly the slope that I just drew, and it could still be optimal, right? If I drew it like this, right? If I drew it like this, both of these indifference curves are going to show that the kink point is my optimal choice. So I'm not going to have, like we would in an interior solution, right, a single marginal rate of substitution that makes this an optimal choice. Instead, what I'm going to have is I'm going to have a range of marginal rates of substitution where every trade that's possible for me makes me worse off. So what does this mean? Well, it means that if I have an MRS that was less steep than the blue budget constraint, right? So if I had an indifference curve that looked like this wouldn't be optimal, right? To have an MRS that's less steep than the blue budget constraint, because then that would mean that I am willing to give up less topping, or in other words, I'm willing to get, say, less than 1/2 an ounce of topping for giving up an ounce of froyo, right? And so I should do that, right? So the first condition is going to be for our middle kink, right? If our MRS was less steep than the blue budget constraint, than the slope of the blue budget constraint, then we would know that the middle kink isn't optimal, right? Because we ought to buy less froyo and more topping. So the first is that our MRS, when calculated at our kink point, right, of 6 and 4, has to be greater than or equal to the slope of our blue budget constraint. Okay. How about if I had an MRS that was steeper than our red budget constraint? Well, in that case, that would mean, right, that I'm willing to give up more than an ounce of topping for each ounce of froyo that I get, or more than 1 micron of topping for each micron of froyo that I get. And I only have to give up 1 micron of topping to get a micron of froyo. So in this case, I should buy less topping and more froyo, right? So this can't be my optimal choice if my MRS is steeper than the slope of the red budget constraint, right? So MRS calculated at the kink point has to be less than or equal to the slope of the red budget constraint. Right? Because otherwise, I would be better off buying less topping and more froyo, right? Less of the vertical good and more of the horizontal good. So what these conditions boil down to, right, is I shouldn't want to give up topping at the price ratio that I would need to have if I was giving up topping, right, the red price ratio. I shouldn't want to get topping at the price ratio that I can get topping at. And because these are different, right, because the price is changing there's a whole range of marginal rates of substitution that make the kink point my optimal choice. So, okay, so when we put all of this together, right, what we're going to say is, if our MRS is so flat that even when we've got no froyo, we still don't want to give up any topping for froyo, we're going to have a vertical solution, right? If it's a little bit less flat than that, we're going to end up finding an interior solution somewhere where our MRS is equal to 1/2 when we're purchasing some amount of froyo and topping where we're no longer getting the discount. If our indifference curves are a little bit less flat than that, right, a little steeper than that, we might get stuck at the kink, right? We might find that we are willing to buy all the topping we can buy for $1 an ounce, none of the topping we can buy for $2 an ounce. They're a little steeper than that, right? We're going to end up on an interior solution in the red part. And if they're even steeper than that, we're going to buy all froyo and no topping. So the way to go about solving something like this, right, with all of these different possibilities, is essentially to try and rule out each of these options until you find something that works. Okay, cool. So that's all I'm going to say about convex budget constraints, right, convex kinks. In the next video, we're going to talk about concave kinks, situations where you get a discount for buying more of some good.